Hello everyone, I'm going to talk about my investigation, evaluation of carbon dioxide capture efficiency using Trona. My name is Santiago Sneider Lopez Delgado, and I was guide for Edwin Alexander Velasco and Edgar Mauricio Morales Valencia. Well, current issue. Climate change is a major global challenge driven primarily by greenhouse gas emissions. Among these, 54% correspond to carbon dioxide. In this graph, you can see the red line and the blue line. The red line corresponds to temperature and blue line corresponds to parts per million of carbon dioxide. Well, uh, Science 2021 global temperature have exceeded pre-industrial levels by more than 1 centigrade. Well, now I want to talk about carbon dioxide capture technologies. Well, in this table, you can see different criteria, and from you can see the normalized wave of this criteria. For example, carbon capture efficiency have 39 normalized wave. Well, I use 5 criteria, the most important, and create this table. This table compares different technologies using these criteria. Well, of this table, you can see the last technology is mineralization. Yes? Well, the mineralization have carbon capture efficiency 80% or 95%. And the different items is low, low, very low. And the TRL is 6. Well, now talk about mineralization reaction with Trona. Well, mineralization is a process to capture carbon dioxide. And this process, mineralization, the earth do this, the process natural, is very natural. Yeah. Well, talk about the trona. This is the composition, and this salt is soluble in a water. Well, the composition of this salt is sodium carbonate and sodium bicarbonate. For this study, I don't have Trona in my laboratory. Now, I use carbonate, sodium carbonate, for the study of this investigation, like a model compound. Well, the reaction for this mineralization technology is that. Well, now the objective for this reaction is determine the operation condition required for reaction to take a place. Well, analyze the effect of initial concentration of sodium carbonate, and well, analyze the effect of the reaction temperature. Well, the reaction was simulated in a semi-batch reactor using ELEC non-random to liquids thermodynamic property method. Well, in aspect class. And in this software, using the electrolyte wizard tool, this tool is very magical. I introduce I introduce species, and well, this software generate different species for these species I introduce. And this is the another data for this simulation, like reactor volume, feed solution volume, gas stream flow rate, and gas stream composition. Well, now take about bench scale process schematic. Well, you can see a gas cylinder, and then you can see a pressure regulator, and then you can see a glow valve, and then you can see gas rotameter. And this is my reactor in laboratory. Yeah. This reactor have a thermocouple, have a magnetic stick bar, have a heating magnetic stir, have a treated gas diffuser, This reactor is a three-neck flat bottom flask. Well, another important topic for this investigation is close the vast magnets. Okay? Well, how is that? Quantification method for carbonate and bicarbonate ions. This is a titulation, okay? I have analyzed, yes. Um, this analyte, I don't know the concentration of carbonate and bicarbonate. Yeah, this concentration is no, okay. Using phenolphthalein indicator and methyl orange indicator, I have a final solution. And with this titulation, I quantify empirical carbonate and bicarbonate ions of this solution. Well, I'm going to talk about results. The first picture you can see carbonate conversion and you can see operating temperature. The temperature increase and the conversion decrease. What is the reason for that? The reason is the reaction irreversible and exothermic. Well, in the second picture you can see carbonate conversion and fixed sodium carbonate concentration. You can see this picture. Yeah. What is this point? 83%. In this moment, the phase is only liquid. The next point, the phase is yeah, the phase is liquid and solid, and this is and the solid phase produce increase to conversion to carbonate. Well, the third graphic Well, the third picture is precipitation phase diagram for sodium carbonate, sodium bicarbonate, and water system. Okay. In this graphic, you can see different zones and you can see lines like 20 degrees, 40 degrees, and others. Well, uh, these lines is a equilibrium liquid solid. Well, and for example, if you have a I don't know, 1 molar and 1 molar of sodium carbonate and sodium bicarbonate in 40 degrees, you have, you stay in this point. E, and the solution is only liquid. If you prepare a solution of 1 molar of sodium bicarbonate and 2 molar of sodium bicarbonate, you stay of this point. Well, in this point, I have a solution with two phases, liquid and solid. Well, this picture is very important. Why? Because in this picture, increased temperature expand the liquid phase ratio. And then operating below 50 degrees promote the selective precipitation of sodium bicarbonate. Sodium bicarbonate have a lot of cost than other salts with this graphic. Um, operate at high initial sodium carbonate concentration promotes the co-precipitation of mixed salts like Trona or Wecherita. Well, the last picture of the simulation, because the laboratory I don't have all results or all points of the results. In this picture, you can see carbon dioxide conversion and time. And you can see different fixed sodium carbonate concentration, okay? For this picture, um, carbon dioxide conversion, it says 18% as long as unrated carbonate ions remain available in the liquid phase. This is the last results. Thank you for your attention.